the example of charging capacitor, yeah, when we charge a capacitor from a voltage here. Okay, for example, there is a switch, and initially it is turned off. When the switch is turned on, it's connecting the whole circuit, yeah, to charge to flow. When is the capacitor will be fully charged? So we solve first. We derive the differential equation using capacitance law and of course also Kirchhoff's law here. So the Kirchhoff current law at point A, yeah, current out equals to 0. So C dVc dt plus Vc minus Vs divided by Rs here equals to 0. So the model here, so we try to make the model into tau dx dt, okay, plus x equals to Fth. So we try to rearrange this equation such that it is in this standard equation. Okay, so RTH C dVc dt plus Vc equals to Vth. Then, so here we multiply each of the term with Rs, so this becomes RTH C dVc dt plus Vc, and then we move these terms Vs into the right-hand side of the equation. So this becomes the Vs become the Vth. Tau here become RTH C. Yeah, assume the Vs equals to Vs. The Vc at 0 condition at t equals to 0 is 0. Then from here, the solution will be Vct equals to the Vs. This is the K1, okay, minus Vs exponent minus t over tau. Yeah, because the T0 is 0. For practical purposes, the capacitor is charged when the transient is negligible. So we here look when tau is, when t equals to tau, then the value of the e exponent minus t over tau is 0.368. When it is to tau, 0.368 square is this one. And when for tau, it is less than 2% of the initial value. Less than 1% error, the transient is negligible after 5 time constants. You see here, this is the graph or the curve of how the transient respond when at different taus, at various different variation of tau. When tau is very small, yeah, like when tau is only 1 second, you see here the upper part, the uppermost graph, that then the system can quickly follow the stimulus. Yeah, the system here means the Vc can quickly be charged by the source voltage. But when tau is very small, very large, I mean, it's 5 seconds, then it will change slowly. Okay, so this happens when in smartphone, old smartphones, they have larger tau. It is why when they are charged, they take longer time before they are completely charged. But today's smartphone, yeah, a newer smartphone, at least in this past year, yeah, when you charge them, even within 1 hour, 2 hours, it will be fully charged, yeah, because then it means that they have very small tau. Yeah, they have been designed, but since the capacitive, they need to charge, they need to store a lot of energy, right? Recent new phones, they have more than 4,000 milliampere hour, for example. So the C value is high, basically. So in order that they still have a small tau, then the resistor have to be made smaller. Yeah, the resistor have to be made smaller. So what they do is they have to make this resistor between the charging and the capacitor, within that the battery, yeah, the RS here smaller, so that then the tau, the overall tau obtained from the R times C will be still small. Okay, so circuit with when we have only one energy storing element, yeah, the differential equation approach. When all independent sources are constant for any variable yt in the circuit, the solution is of the form like this, yeah. So this is what we have derived earlier. So from the solution for first differential equation. But this is the specific case where we have the independent sources are constant. So the right-hand side of the differential equation is the constant, which when it will the FTH will becomes the K1, which is the steady state value. And the steady state value when t approaches infinity. So the condition here that the circuit has only constant independent sources. The differential equation for the variable of interest is simple to obtain. Yeah, using basic equation, Kirchhoff current law, Kirchhoff voltage law, or using Thevenin's law, etc. What you have learned in semester 1. Then what is also important that the initial condition for that differential equation should be known also. That can be obtained using steady state analysis. So after you derive the equation for that particular circuit, you need to rearrange it such that it will be expressed in this standard form. Sorry, the previous standard form, like this, yeah, tau dx dt plus x equals to the forcing function. The forcing function here, if it contains only constant independent source, it will be a constant. Okay. Use the differential equation and the initial conditions to find the parameters K1, K2, and tau. If the differential equation for y is known in the form of A1 dy dt plus A0 y equals to f, yeah, then the initial condition is also known at t0, t equals to t0, why not? Then we can use this to find the unknowns. Okay, use the differential equation to find two more equations by replacing the form of solution into this differential equation. So here then, if our solution is in this standard form, yt equals to k1 plus k2 times exponent of minus t over tau, yeah, at t larger than 0, then dy dt from this will be, this dt will be 0 because this is a constant. These terms derived in respective to the time will be equal to minus 1 over tau, right? Minus 1 over tau times k2 exponent minus t over tau. So from here, we obtain here, then we insert into this equation. So this becomes a1 minus k2 tau over tau exponent minus t over tau plus a0 times the value of y, yeah? A0, k1 plus k2 exponent minus t over tau equals to f. From here, we obtain A0 K1, this one, will be equals to F, yeah, with K1 equals to F over A0. Okay. So from here, then also minus A1 over tau plus A0 minus A1 over tau plus A0 K2 exponent minus T over tau will be equals to 0. Yeah, with tau equals to A1 over A0. This value, yeah, from the equation. So use the initial condition to get one more equation, which is y0 equals to k1 plus k2. Yeah. y0, y0 equals to k1, k2, because at t equal to 0, yeah, here, t equal to 0, this exponent term becomes 1, right? So y0 equals to k1 plus k2. Okay. So from here, then k2 is equals to y0, the initial value at 0, minus k1. So write differential equation in normalized form, so like this, with coefficient of variable equals to 1. So it is like this. Then a1 dy dt plus a0y equals to f. We divide by a0, so that then we express the equation as a1 over a0, okay, dy dt plus y, yeah, equals to f divided by a0, and this is equals to tau. So this is basically the same as the previous standard equation, yeah, the previous standard form of equation in this one are we express as tau dx dt plus x equals to the forcing function, the new FTH. Okay, so the variable or the constant that is multiplied to the first derivative of the variable will become the time constant, the tau the tau dy dt, yeah, which is from tau will be obtained from a1 divided by a0. So the factor that is multiplied to this y should be made into 1 divided by a0, like this. So this is the standard form now. And then from here, we obtain a1 divided by a0 as the tau, and this f divided by a0 as the k1. Okay. So this occurs when at constant, yeah. So when y equals to f divided by k1. For clarity, let's just try to solve several examples. Find here the voltage at the capacitance value Vt here when t is larger than 0. So from the switching, we know that when t is larger than 0, that the switch is turned on. And when the switch is turned on, it means that the capacitor starts to be charging. Yeah, the current will flow, and the Vt will immediately increase from 0 until certain value. The V output here is Vs divided by 2. Not V output, V0. Yeah, the V at time 0 here equals to Vs over 2. So it has already an initial condition of Vs over 2. So first, the solution will be in the standard format. Yeah, here, xt equals to k1 plus k2 exponent minus t over tau at t larger than 0. Then when k1 will be the value when the t is approaches infinity. Yeah, when t here approaches infinity, and then this value will approach to 0. Exponent minus infinity is 0. Yeah, so if you try to graph exponential term, if this is t and this is exponent minus t, okay, when t is towards infinity, then this becomes smaller and smaller until it approaches 0. So that is why when t approaches infinity, this becomes 0. So xt becomes equal to k1. So k1 basically is x at t equals to infinity. So k1 plus k2, on the other hand, yeah, when t is at equals to 0, this terms, yeah, this becomes 1. So this one, when t equals to 0, this intersects the y-axis at 0 at 1 point. Okay, so it means this is x at 0 equals to k1 plus k2. So for t larger than 0, let's use Kirchhoff current law. Okay, let's use Kirchhoff current law at voltage, this one, voltage t. Okay, similar like in the previous slide. So dvc dt, use the capacitance law, the differential form of capacitance law, Vt minus Vs divided by R plus C dV dt equals to 0. Okay. The initial condition for the voltage at 0 is Vs equals to 2. This is something which is given by the problem. Okay, not something that we derive from the circuit, but something is given in the problem. What is the initial condition should be given. Otherwise, we cannot solve the graph, because this will set the condition for K1 and K2, for K1 and K2 later, the constant. So the differential equation is known, and then initial condition is also known. Step 1 is time constant. We find the time constant first. So we have to re-express this initial condition into this standard function, the standard form of the differential equation form. Tau dy dt plus y equals to f. Okay, so it means this one dy dt represents represent this dv dt. Okay, so each term of this is multiplied by r, so this becomes Vt minus Vs plus Rc dv dt. Okay, Rc dv dt plus Vt, and Vs we move to the right hand side of the equation. Okay, it becomes like this. So now this form resembles this form. Yeah, from here then we know immediately that the tau equals to Rc. Yeah, that's simple. Any questions so far?
No, sir.
No, sorry. Okay, it's quite clear. Yeah, I think so. The important thing is derive first using KCL and rewrite the initial condition based on what is given by the question. After that, you rewrite the equation here into the standard form tau dy dt plus y equals to f, equals to forcing function here. Yeah, after you, for example, here, in order to make it in this form, you have to multiply each term with R, with the resistor. Yeah. So because what you want to, you have to have one term, which is that variable that you want to know. In this case, it will be Vt. Yeah. In this original KCL, the Vt is still divided by R. So in order to have Vt, you have to multiply by R. So this is if you ask why we have to multiply by R. Because we want to have the Vt multiplied only by 1 as the multiplying factor. Okay, tau equals to Rc. Then get time constant as the coefficient of the derivative. Yeah, the coefficient of this derivative dv dt, Rc. So step 2 is to do the steady state analysis. The steady state analysis when t approaches infinity. Okay, and that is the steady state value. So from here we know that steady state response is obtained when t approaches infinity. When t approaches infinity, these terms become 0, right? So xt will be equals to k1. So the solution is Vt plus equals to k1 plus k2 exponent minus t over tau for t larger than 0. For tau larger than 0, for tau is positive and the tau value is positive, and t approaches infinity, then Vt will approaches to k1. This will be the steady state value. In steady state, the solution is a constant. Okay, in steady state, the solution is constant, K1. That is why the derivative will is zero from the differential equation. Yeah, if dv dt, so dv dt dk1 dt, since it is a constant, will become the dk1 dt is zero. So it means then dv dt should be zero. Okay? Dv dt should be zero. This one should be zero, right? Since it is at infinity, steady state value. So it doesn't change anymore with time. Dv dt equals to zero, it means Vt equals to Vs. Yeah, the steady state value from this differential equation. So from here, then, from the general value of solution, we obtain Vt at t infinity. The t approaches infinity, Vt equals to K1. And from this differential equation, when dv dt equals to zero, yes, it's the steady state, when Vt equals to Vs, then K1 equals to Vs. And we equate these two equations. If the model is tau dy dt plus y equal f, then K1 equals to f. Why? Yeah, because the dy dt here at infinity is zero. Dy dt is zero already, so it means y equals to the f. It means since from the general solution here, yeah, at t infinity, the value is K1, it means then K1 equals to F. F here is the forcing function. Now, we use the initial condition to calculate K2, the second constant in the general solution. Xt equals to K1 plus K2 exponent minus t over tau. So at t equals to 0, yeah. So here t equals to 0, Vt will be equals to, this is equals to 1, yeah. So Vt equals to K1 plus K2, okay. K2 will be equals to the V0, the initial condition, minus K1. K1 here is already known as Vs, and the initial condition of voltage is also given by the problem. It is also known. The V at 0 is Vs divided by 2. So K2 will be equals to Vs over 2 minus Vs. Yeah. From here, when we obtain K2 to be, so V0 is Vs over 2, then K2 is V0, this Vs over 2 minus F, and F is Vs, right? So K2 equals to negative Vs over 2. Okay, any questions so far? So here, from here, we already obtained from the step 2, yeah, the steady state analysis, K1 value, which is Vs. From the step 3, using the initial condition, we obtain K2, yeah, minus equals to negative Vs over 2. So basically, we already obtain our solution. So from the first step, also we already obtained the time constant tau. Okay, so to summarize, first step we obtain tau. Second step to obtain the steady state analysis, using steady state analysis to obtain K1. This is the constant of the general equation that doesn't vary with time. And using initial value, we obtain the K2. This is the coefficient of with the time varying value. This one. So here we already then get the solution that the answer will be Vt equals to, okay, let me erase first. Vt equals to the general solution, K1 is Vs, K2 is negative Vs2, so negative Vs over 2 exponent minus t over tau, and tau is Rc, okay, Rc. This is the general solution for this circuit. Okay. Any questions so far? So again, to summarize,
Yes, yeah. What is F?
F is the forcing function here. So the F here represents a forcing function due to this voltage source. Yeah. So first, if you derive the equation for the circuit using Kirchhoff current law, you obtain this one, right? Vt minus Vs over R C dV dt over C dV dt equals to 0, right? Because from this node, you have to rewrite this such that it represents this general form of the differential equation. This is a general form of differential equation. If it could also, we could also have case where there is no forcing function. So in this case, it will be tau dy dt plus y equal to 0. So in this case, f equals to 0. When is it? When will we have such case? Anyone can answer? When? This is, yes?
Voltage
Yes.
source.
Yes, when it is short-circuited. When this is short-circuited, right? When we don't have any voltage value here, when Vs equals to 0, basically short-circuit, that is when the F is 0. So we don't have a forcing function. We call it that in differential equation as forcing function, as the constant. That will form the K1. So it means the general solution later, we will have this will be equals to 0. The Vs will be, the K1 will be equals to 0. If K1 equal to 0 and the initial condition, for example, is Vs over 2, so K2 will be equal to initial condition Vs over 2. Okay, so we will only have, instead of like this, we will only have Vt equals to Vs, no, this is 0, right? So we will only have Vs over 2 exponent minus d over Rc, like this. If the Vs is just short circuited, so we have only this kind of circuit. Okay, with only R and C, and initially they are disconnected. Somehow the C is already have initial value of voltage, yeah, Vs over 2. Vs is some value. Okay, so yes, so when we have Vs, like what is presented in this line, so when first we have to eliminate this denominator, right, by multiplying each term with R. Okay, so R multiplied by this becomes Vt minus Vs plus Rc dVt dt. Then the Vs term, then it is not the variable that we want to calculate. We move to the other side of the equation. Yeah, in this case, the equation becomes this Rc dVt dt plus Vt equals to Vs. So if we compare with this general form of differential equation, so this is the coefficient that is connected, yeah, multiplied to the derivative term, yeah, this one. So the Rc here, it becomes the tau. And this is the variable that we want to seek, yeah, to calculate. The coefficient has to be made 1 in this particular standard form. The part on the right hand side equation will be the forcing function, and this one will be the Vs. Okay, and if we compare with later with the standard equation, the standard solution, which is xt equals to k1 plus k2 exponent minus t over tau, yeah, then we know that k1 is the steady state condition, yeah, when t equals to approaches infinity. So this becomes 0, these terms become 0, and then xt becomes k1. Okay, basically it is equals to the forcing function, yeah, because at steady state the dy dt, the voltage variation over time is zero, no variation anymore. That's why it is called steady state. Yeah. Then the value will be equal to f, the forcing function. So from there we know that the k1 value equals to the f, the forcing function, Vs. So the Vs will be the steady state value. So far, understand sampai who are asking, who's asking just now? Osama, is it?
Yes, sir.
Do you understand?
Yes, thank you.
Okay, I hope. So let's take a break first. Yeah, there's a lot of mathematics for now. Let's have a break and wait. So please fill in the. Okay, everyone still here?
Yes, sir.
Okay, good. Okay, so this is another example. Yeah, when this now instead of capacitive circuit, we have inductive circuit. Find the current IT when T is larger than 0. And from the problem here, we know that at T equal to 0, the switch is turned on. Yeah, the switch is turned on. So it means that at T equals to 0, current starts to flow. Yeah, in inductance, what is continuous is the current. Remember this basic form of the solution. Okay, we can actually derive it, but since we are not in calculus class or engineering mathematics class, this actually derived in the previous slide, but in quicker manner. Yeah, if you want more formal mathematical derivation, please refer to the explanation by Pak Agus or Pak Fatani in the other subjects. So for now, yeah, for this electrical engineering, it's better we just memorize this, the basic form of the solution for first differential equation. Yeah. Xt equals to K1. This is the steady state solution constant. Yeah, because when T approaches infinity, this term becomes 0. K1 plus K2 exponent minus T over tau. And K2 comes from the initial value, yeah, and K1. K2 is calculated from initial value and K1. So at T equals to infinity or approaches infinity, Xt will be equals to K1 here. At T equals to 0, the initial value, so X0 equals to K1 plus K2. So please remember this, memorize this. So this is the solution when you already derive the equation and then re-express the equation in the basic form. Yeah, the basic form will be tau dx dt plus x equals to f. Okay, this is the basic. You have to express the equation of the circuit in this basic form. So later from here we find tau. From the second step, the steady state analysis, we find K1 equals to F. From the initial value analysis, we will find K2 equals to an initial value X0 minus K1. Okay, so this is how we solve the problem in general. Okay, so in previous example, we solve capacitive RC circuit. Now, what if we have RL, inductive circuit? So in this case, then we express the solution in terms of the current, yeah, because remember that from the previous chapter in inductance, it is current that is continuous. So here, instead of solving for voltage, we solve for the current that flows through the inductance L. IT here equals to K1 plus K2 exponent minus T over tau. Now let's find K1, K2, and the tau. Let's first derive the model using Kirchhoff voltage law for t larger than t0. So when t larger than than 0, then the switch is turned on. Okay. Then from here we obtain Vs equals to Vr plus Vl. Okay. Vs equals to Vr plus Vl. Vr equals to the current times the resistor from Ohm's law. Then the Vl we can calculate from the differential form of inductance law. Vl equals to L di dt. Okay. So hence the initial condition for t less than 0, yeah, at the current, when the current is at 0, the current is t equals to 0 from the left side. Yeah? So before, just before the switch is turned on, is 0. Okay, so it means no current is flowing through the inductors. So since in inductor, you remember that current has to be continuous. Yeah? Well, in capacitance, voltage is continuous function. So if it is continuous, you cannot have disruptive values approaching the t equal to 0. Okay, so the current at 0 approaching from plus from the right, this one has to be equal to the current at 0 approach from the left, yeah, from minus infinity. So it means from this condition, the current at 0 from the positive just after, it means here, if we express this physically in the physical meaning, the current at the inductance just after the switch is turned on should also be equal to the current just before the switch is turned on. So it means I0 plus equals to 0 also. Okay.
I'm sorry to interrupt, sir.
Yes.
Osama is not in the room, he's in the waiting room. He accidentally get out, I think.
Yeah. Okay.
Thank you, sir.
So please do not go in there, because otherwise the class will be interrupted. So again, the current is continuous, so it means that the current just after switching equals to the current just after switching equals to the current at the inductance just before switching. Okay, so because the current has to be continuous, so it doesn't mean that when the switch is turned on, immediately the same current that flows through the resistor will flow through the inductors. No, the current will increase gradually at the inductor. Yeah. Resistor, since it is not a charge, it is not an energy storage element, current will just flow through it and dissipate it into heat. But inductors is different. Capacitance is also different. So here again, when it is just switched on, the current at the inductance, it's not immediately equal to the current flowing through the resistor. Yeah, because it will change with time. But the initial value will be equal to the just of the current at the inductance just before the switch is turned on, which is 0. Okay. So then step 1 is to re-express the equation. This equation, yeah, Vs equals to Ri plus L di dt in the general format of this one, tau dx dt plus x equals to f. Yeah, so it means that the coefficient of the parameter we want to seek has to be 1. In this case, it is current. The coefficient has to be 1. The current, this equation, however, still has the coefficient of I is R, the resistor. So we have to divide this with R. Okay, so it becomes IT. It means the other terms have also to be divided by R. So this term becomes L over R di dt. This term becomes Vs over R. So this is why we obtain here from here to here, L over R di dt, which is this basic term, yeah, tau dx dt, plus IT, similar to this basic standard form, X equals to Vs divided by R, which becomes the forcing function F. Okay, so from here we already obtain the tau equals to L over R. Okay, for our general solution here. Okay, tau equals to L over R. For step 2, we want to find the K1. Okay, this is the steady state constant when t equals to or approaches to infinity. So here, when t approaches to infinity, it means IT will be equals to K1. And if we go to the differential equation, when t approaches infinity, when it is steady state, there is no more change of current with time. So di dt will be equals to 0. If di dt equals to 0, the IT equals to Vs over R, right? IT equals to Vs over R equals to K1. So it means K1 equals to Vs divided by R. Yeah. Okay, K1 I at infinity here equals, when t approaches infinity here, this value becomes 0. Yeah, becomes 0 when t approaches to infinity. So I infinity equals to K1 equals to Vs over R, because this one also di dt should be equals to 0 when t approaches to infinity. No more change of current with time because it is steady state. So we find now K1. To calculate K2, we have to use this initial condition. I0 equals to 0. Okay. So at t equals to 0, at initial condition, this t equals to 0. So this term become 1. So I at 0 equals to K1 plus K2. This one, yeah. Since I0 plus here equals to 0, 0 equals to K1 plus K2. So it means K2 equals to 0 minus K1. Yeah, so from here, K2 equals to I, 0 plus minus K1. I0 plus is 0, 0 minus K1. K1 is Vs over R. So K2 equals to minus Vs over R. Okay, so if we then put these constants K1, K2, and tau into the basic standard form of the solution, we obtain here IT equals to K1 is Vs over R multiplied so IT equals to K1 is Vs over R plus K2, K2 is minus Vs over R exponent minus T over tau. Tau is L over R. Yeah, so we can simplify this into Vs over R 1 minus this one exponent minus T over L over R, which is this form. See, any questions? Quite clear, yeah, I think. Okay, let's do some example now. Find the current T for T larger than 0 in the following network. So now the resistor is put in parallel with inductance, and the switch is turned on between the resistor and inductance at T equals to 0. And they are connected to a constant current source Is. So first, what we want to find is Ip, the current flowing through the inductance L. And so this is the basic solution. It equals to K1 plus K2 exponent minus T over tau at T larger than 0. The model for the KCL for T larger than 0 is that using Kirchhoff current law, Is equals to Vs over R, the current flowing through the resistor, plus It, the L. Yeah? And we know It here can be obtained using the integral form of inductance, yeah, 1 over L integral V dt, yeah. Vt here equals to then L di dt. So then we can re-express the equations inside the blue box becomes S equals to Vt here expressed, re-expressing Lr di dt. No, apparently we don't need to use the integral form. We just use this one plus it. Okay, so this one still in it, we express Vt here in terms of the differential form of inductance law, L over R di dt. Okay, so this is basically already in the standard form of the equation, of the differential equation. So the initial condition is known. So the current flowing through the inductance when just after the switch is turned on is equal to 0 because it should be the same as the current at the inductance just before the switch is turned on. So from here, we immediately obtain tau equals to L over R. Okay, step 2, we find the steady state solution when t approaches infinity. So di dt will be equals to 0. So it equals to Is, and this equals to K1. Okay, so K1 equals to the Is, the value of the current source. At the step 3, then we try to find the initial condition. Is, yeah, the current at 0 plus equals to 0, and this equals to K1 plus K2. Yeah, so it means K2 equals to 0 minus K1, which is equals to minus Is. So from here, we obtain the answer IT, the current flowing through the inductance, equals to Is times 1 minus exponent minus T over L over R. Is it clear so far? Any questions? Okay, yeah. Okay, so I think these are now exercises, I think, until an example. Yeah, it's okay. Let's just do this. Yeah, let's just do this. In quicker manner. Assuming that the switch has been in position 1 for a long time, at time t equal to 0, the switch is moved to position 2. Okay, we wish to calculate the current IT for t larger than 0. So in this case, then before the current doesn't flow at t before t equals to 0, the switch is at position 1. So the current doesn't flow through the voltage flows through the capacitive, yeah, to charge it. Okay, the current also flows through the R2. When the switch is turned to position 2, it is disconnected from the voltage source. So now the charge in the capacitor will be discharged. Yeah, so the capacitance will become a voltage source with a varying value. So calculate now the current IT, the current that flows through the R2. The R2 here basically represents the load, 3 kilo ohm load. So for t larger than 0, this is the model, the circuit model. So we can express this in the standard solution of differential equation, IT equals to K1 plus K2 exponent minus T over tau. So we need to find tau, we need to find K1, and we need to find K2. Okay, so it will be simpler to determine the model for the capacitor voltage instead of current. because voltage is capacitive is with capacitance, the continuous part is the voltage one. The continuous parameter is the voltage. So, and then that is why then we can use the differential form of the capacitance law. So expressing the current in terms of voltage, IT equals to Vt divided by R2. Okay. Using Kirchhoff current law at Vt, Vt so here Vt divided by R1, current going out to R1 equals to C dV dt plus Vt divided by R2. So equals to 0. So current flowing out of the branch should be equal to 0 from Kirchhoff current law. Now here, the R1 and R2 are basically in parallel to each other. So we can simplify them into a single parallel, equivalent parallel resistance, RP. So then we can simplify them into this equation becomes C dV dt plus Vt divided by Rp. And the Rp equals to 3K times 6K divided by 3K plus 6K. Okay, 18 divided by 9 is equals to 2 kilo ohm. Then the initial condition is found when the switch is still in the position 1. When the switch is still in the position 1, we want to know Vc at the 0 minus, which is basically equals to this position, which is this becomes a resistor voltage divider. Okay, the Vc at 0 minus, so the voltage at capacitor just before the switch is turned on equals to 3K. So remember that when it is a DC voltage, right? In this condition, there will be no current flowing through the capacitors. There will be no current flowing because this is a 12 volt is a non-varying voltage source. So it means that the voltage at the capacitor equals to this voltage division 3K divided by 3K plus 6K times 12. 1/3 times 12 equals to 4 volt. So the voltage equals to 4 volt. The step 1 we try to find the tau. Okay, the tau equals in this case from this equation. Okay, so we can re-express the equation. So this becomes multiplied by Rp to make it as a standard equation. So Rpc dVt dt plus Vt equals to 0. So in this case, the forcing function is 0. This is like what I've explained in the earlier session, that when like this condition, then there is no forcing function because it is not connected anymore to a voltage source. The voltage source function here just to give the initial condition. So from here, then we obtain the tau, equals to the Rp times C, 2 kilo ohm times 100 microfarad equals to 0.2 second. Step 2 is to find the steady state analysis, when t equals to t approaches minus t approaches infinity, when the current equals to sorry, in this case is voltage, and the voltage equals to infinity, steady state time equal infinity. So it means dV dt equals to 0. So we obtain Vt equals to 0. V infinity equals to 0 equals to K1. So K1 equals to 0. Then the initial value analysis, V0 plus equals to here equals to K1 plus K2. Because here V0 plus equals to K1 by K2. And this equals to 4 volt obtained from this solution. So from here we obtain K2 equals to 4 fold minus K1. Since K1 equals to 0, K2 equals to 4-fold. So from here we obtain the solution Vt equals to, since K1 equals to 0, only K2 remains, so only the transient response occurs. Yeah, Vt equals to 4 exponent minus t over 0.2. But this is still voltage. What is being asked is the current. So we have to put here IT equals to Vt over R2. So we have to divide this with R2 value, which is 3 kilo ohm. Okay, and the value becomes milliampere. Be careful with the unit here. From volt divided by kilo ohm, so becomes milliampere unit. 4 over 3 exponent minus 3 over 0.2. Okay. Okay, another example here. We have here the switch is turned off at t equals to 0. There are two voltage sources. Yeah. Now, what is the value of V output here at t larger than 0? Okay. So first, this is again, remember this general form of the standard form for the solution of differential equation. Xt equals to K1 plus K2 x1 minus t over tau. Okay. Then K1 represents the solution at infinity, and the solution at initial value x0 equals to K1 plus K2. Okay, this general standard form. So when t larger than 0, the switch is turned off, cannot connecting. So at that moment, it means that the inductance here will discharge its current, but there is still here connecting 12-volt source from the VS1. Use KVL for t larger than 0, Okay, so this is switch off. So we only have the outer larger loop. The current that flows through the 12-volt, the R1, L, and the R3. So from here, we obtain minus VS1, using Kirchhoff voltage law, minus VS1 plus R1 R1 IT plus L di dt here plus R3 times IT equals to 0. Okay. So here we simplify further. Okay. L is 2 Henry, 2 di dt plus R1 and R3 can be made into a single series resistor. 2 plus 2 becomes 4. For IT equals to NVS1 is minus 12 volt, and we move to the right hand side of the equation equals to 12. And the final value which we want to find is the V output at R3, so which is equals to 2 ohm times the current, or 2 times IT. So going back to the differential equation, so this is not yet standard form. So we have remember that the coefficient to the variable that we want to find the value must be 1. So we have to divide this equation with 4. So that then IT, the coefficient of IT becomes 1. So this becomes 0.5, half the IDT plus IT equals to 3. 12 divided by 4 is 3. So from here, then we can find now this tau will be equal to 0.5, right? Tau equals to 0.5. Okay, the step 1. Step 2, to find K1, the steady state value, the steady state analysis. So the IDT will be so from here from the IDT, we change to the form of V output. Since V output equals to 2 times IT, we obtain, so it means we can change I here with V output, the V out dt plus half the V out dt plus V V out dt equals to 6 volt. Yeah, 6 volt here comes from this 3 times 2. 3 times 2 equals to 6 volt. Okay. Then yes, tau is 0.5. We obtain like this. We try to find the K1 using steady state analysis. 0.5 dV out dt plus V out t equals to 6 from here. V out at infinity, which is K1 at infinity, there is no dV out dt anymore. dV out dt will be equals to 0. So V out t, V out at infinity equals to 6 volt. Yeah, from here V out, and this basically equals to K1. So K1 equals to 6 volt. The next step to calculate K2, we need the initial value of V out at just when the switch is turned off here. So for the initial condition, one needs the inductor's current for the t less than 0 and uses the continuity of the inductor current during the switching. Because in inductor, the current is continuous. The steady state assumption for t less than 0 simplifies the analysis. Steady state assumption means at t less than 0, since this is this is direct current, direct voltage, we can assume, we can simplify inductance model as short circuit, right? As short circuit. So here we find a short circuit. We try to find this AL at t less than 0. We can use we can simplify here further. So this becomes this is 2 ohm. Simplify into 4 volt. Okay, this value. 2 volt. This is simplify. This is a parallel, basically a parallel resistor. That becomes 1 ohm. Use Thevenin, a summing inductor in the steady state. Here in the steady state means that it will be in short circuit. The resistor with 0 value. As a Thevenin, then we find the Thevenin equivalent voltage is 4 volt. The Thevenin equivalent resistor at this node is 1 ohm. Okay. So from here, then we calculate the R Thevenin. From here, the R Thevenin of this V open circuit is 4 volt. The R Thevenin from here is 2 parallel to 2. We remember, we assume that the voltage are in short circuit, so we find the R Thevenin to be 1 ohm. And the V open circuit here can be calculated using this Kirchhoff voltage law. Minus 12 plus 4 times I1 minus 4 equals to 0. We obtain I1. I1 to be equals to 12 plus 4 is 16. I1 equals to 4. Okay, 4 ampere. 4 ampere. So VOC equals I1 is 4 ampere. Using Kirchhoff voltage law here, we can obtain V open circuit at this node, AB node. 4 times 2, it's 8. 8 minus 4 is 4. So we obtain the V Thevenin, or the V open circuit is 4 volt. So we replace the whole circuit here on the left side of node AB as Thevenin source 4 volt with equivalent Thevenin resistance of 1 ohm from here. And this is connected to the 2 ohm resistor. Then we can calculate the current of the inductance at 0, which is basically 4 volt divided by 1 plus 2, 4 divided by 3, 4 over 3 ampere. So the current at the just before the switch is turned on will be equals to this current just before the switch is turned off. It is 4 over 3. It means the V output at the 2 ohm equals to 4.3 times 2 ohm equals to 8/3 volt. Yeah. Okay, so then we can insert this 8/3 volt into the previous standard equation. We know the K1. Yeah. Yeah, the K1 equals to 6 volt. 6 plus K2 equals to the V output at plus here, which we have calculated just now using the Thevenin equivalent circuit. 8/3. Yeah, K1 plus K2 equals to 8/3. So this 6 plus K2 equals to 8/3. K2 equals to negative 10/3. So the solution will be then K1 6 minus 10/3 exponent minus t over tau, which is 0.5. Okay. Yeah, in this case, then the difficult part is to find the initial condition. Yeah, such that we can calculate K2, yeah, the constant of the transient constant. So from here, then we can obtain the current also divided by 2. Yeah, 3 minus 5/3 exponent minus t over 0.5. I think, yeah, this is something also the same. Yeah, so I will skip this running extension and go towards the this part in this using Thevenin to obtain the model. Okay. So when we have let's skip this. So initially we have how to use the Thevenin to obtain the models. When we have a circuit with resistances and source, and then it is connected to an inductor or capacitor. Yeah, so this is the representation of an arbitrary circuit with one storage element. Obtain the voltage across the capacitor or the current through the inductor. Because in capacitor, it is the voltage that is continuous, while in the inductor, it is the current that is continuous. Then, using Thevenin approach, the circuit with all the resistances and sources can be replaced with equivalent Thevenin source and connected in series with a equivalent Thevenin resistance. Then, when it is voltage across capacitor like this, case 1, and case 2 is when it is connected to inductor. Yeah, then we calculate the current through that inductor. We can use KCL at node A in this first case. Yeah, IR equals to IR plus IC equals to 0. Okay, in which IC equals to C dVC dt. Then in IR equals to VC minus VTH over RTH. So this is basically the same like the earliest example we give when the voltage source is just connected to R and C in series. Then C dVC dt, then we put into the standard form. Yeah, C dVC dt plus VC minus VTH over RTH equals 0. We multiply both sides with RTH, right? To obtain the standard form here, RTH C dVC dt plus VC equals to the VTH, the Thevenin form. In the inductor case, we use KVL, VTH plus VR plus VL equal to 0, or VR plus VL equals to the VTH. VR plus VL equal to the VTH. VR equals to the RTH times the IL. the inductive current, the current flowing through, because it is basically in series. And VL equals to L di dt, DIL dt. So okay, then the KVL we can express using the differential forms of the capacitance law, L DIL dt plus RTH IL equals to VTH. Yeah, and then we define, yeah, we have to, in order to make it into the standard form, we have to make the coefficient of IL equal to 0, equals to 1. We divide each terms with RTH, L divided by RTH DIL dt plus IL equal to VTH divided by RTH. So, and we know that the VTH over RTH, yeah, VTH over RTH is basically the same as the current when it is short-circuited, right? When it is short-circuited, that's why it is equal to ISC. This is one example, like this. The switch here is switched off when T equals to 0. The variable of the interest here is the inductor current. So we have to replace all this, the circuit, yeah, just connected to this inductor with one single equivalent Thevenin source and one in series with one Thevenin resistance. Okay, the model will be L over R DIO dt plus I0 equals to the VTH over RTH. The solution will be in the form here. This is the standard form of the solution of differential equation as we have explained earlier. So I0t equals to K1 plus K2 times exponent minus T over tau. So the Thevenin for T larger than 0 at the inductor signal is shown is like this. So here it is already disconnected. So it means the VTH, the V open circuit is 0. Okay. Why it is 0? Because no, this is not connected, right? No connected, so no current flowing through these resistors as well. So that's why the voltage here is also 0. Now, what is the resistor, the equivalent Thevenin resistor? We just use the series and parallel. Yeah. So this will be 6 here plus 6. 6 plus this 6 plus 6 is from here in parallel with the 6, yeah, here, then in series with the 6. Okay, so we obtain the value to be 10 ohm, and the tau is equal to the inductance value 3 Henry divided by 10 ohm, or 0.3 second. So we can put this again to this equation, 0.3 DIOs dt plus IO equals to 0. Okay, the VTH, the voltage of the Thevenin is 0. From here we obtain 0.3, and K1 will be 0, yeah, because there's no forcing function. The value at infinity, since it will be 0, I0 with IO will be 0 also. And now we try to find K2. Okay, then K2 will be I0t will be K2 exponent minus T over 0.3 at T greater than 0. So we are left with the last step, which is to find the initial condition at this I0t. So here we have to find to determine the current when it is before the switch is turned off. Okay, so it means when the current is still flowing here, we can, yeah, the I0 from the left equals to I0 I output from the right. So like this. So we can use mesh analysis. Yeah, and since it is in steady state, we assume that the inductance is modeled as zero resistance. Okay, as zero resistance. So from here we obtain 6I1 plus 6I1 minus 3. I think this is in this loop, yeah, plus 6I1 minus I2 equals to 0. And the second loop here in this loop, minus 24 plus 6I1 minus I2 here, plus 6I2 minus I3 equals to 0. And the third loop here, 6I3 minus I1 here, plus 6I3 minus I2 equals 0. And we solve, we find here IC, the current at L equals to the I3 here, okay? We solve using loop analysis from 3 simultaneous equation, yeah. Then I0 at I output at 0 plus here will be equals to this one. This is basically the 24 plus divided by 6 plus V1 here divided by 6. So the current flowing through here. Okay. So using this is the node analysis where we obtain V1 to be equals to 8 volt. Node analysis at this value, I think V1, yeah, this node V1 over 6 plus V1 over 6 here, okay, plus V1 minus 24 over 6 equals 0. So we obtain V1 equals 8, and we obtain from here, then we obtain IC at 0 plus just after the switch is turned off equals to 32 over 6 milliampere. Since K1 equals 0 from the previous slide, then the solution will be I0t equals to K2 exponent minus T over 0.3. And we just evaluating at 0 plus, yeah, we obtain this, we insert this value, substitute this value to here, okay, and we obtain K2 equals to 32 over 6. Okay. Okay, so let's